Good evening, everyone. So, welcome to the sixth weekly live session for the course Geomorphic Processes, Landforms and Landscapes, which is taken by Professor Javed Malik from the Earth Sciences Department in IIT Kanpur. So, till now, the first the first two live sessions were actually on the basics of the course geomorphic processes and some basics about the earth structure, the different tectonic processes that take place, and landforms and different kind of features that are associated with them. Then we went deep into understanding fluvial geomorphology and the different geomorphic landforms that are created due to the action of the rivers, running water rivers, and we understood some of the aspects of how the erosion and deposition is carried out by the rivers and associated landforms and landscapes that are created by them. So, that was one natural agent which causes changes on the land on the surface of the earth. Now we will move on to different kind of geomorphology. So, this is not essentially due to the action of one certain uh, say natural agent which is actually uh, changing the geomorphology of an area. So, when we talk about tectonic geomorphology, it is usually a combination of the different tectonic processes that are happening in that area, as well as the surface erosional and depositional and weathering processes that are taken care or that take place due to some other natural agent. So, for example, if at in an area you have a river flowing across that area. So, if there is an area where the river is flowing over the land and that area is getting, it is changing its landscape due to the flow of the river, as well as some tectonic processes are also active in that region. So, the geomorphology or the geomorphic landforms that will be created in that area would be a combination of these two processes. So, tectonic geomorphology is usually the combination of the tectonics as well as another surface process that is taking place. It can be created mostly we would be seeing that these tectonic geomorphic processes are more active in areas where you have mountain building. In the mountainous regions, mountain building tectonic processes are mostly active. So, in those areas, as we had seen in the fluvial geomorphology part, that most of these areas are governed by either glacial the action by glaciers or running water, that is rivers. So, when we are talking since mountainous areas are usually active in their tectonic setup, okay, so usually some or the other tectonic processes always active in these regions. So, you can we will try to understand tectonic geomorphology with the combination of the tectonics that is happening in such areas, as well as mostly we will be trying to understand how the fluvial processes also are acting in those areas. And then we will see that some landforms that are created due to tectonic geomorphic processes is different than what we see in what we had seen in the fluvial geomorphology part. So, this is a basic understanding of what tectonic geomorphology would be, and usually these have a very different time scale of occurrences. So, sometimes if the tectonics the movement in that area due to tectonic processes is rapid, so it can range up to days, and if it is a long occurring process, or the event is a very slow process, then it can take years. So as we have said that the time scales for this would range from days as well as to millions of years for such geomorphic processes to change the landscape in the area. So as I said that the evolution of any landform, it can like when we are talking about your tectonic geomorphology, it's a combination of climatic, tectonic as well as surface processes. Okay. So if I zoom into this a bit, so you can see that this is of a faulted glacial moraine part. Okay, so we have not yet done the glacial geomorphology part till now, but this is just an example of how glaciers themselves, which are actually generated or which are forming in such active tectonic areas, how they accompanied with tectonic processes can change and form different landforms over here. So this over here you can see that a lot of ridge kind of features are over here. So these are your moraines. Okay, and then you have obviously grabens and valleys that are forming here. Then you have something called triangular facets, which we will be learning in the upcoming slides. And then you have grabens are a kind of feature, those are formed due to faulting processes, so we will see that also. So this is just an example of how the combination of glacial geomorphic processes along with your tectonic geomorphic processes can form the different features. The first landform or the first geomorphic feature that we can study, or that can be classified under tectonic geomorphology, is called an escarpment. So it is actually, if I draw this part, okay, this area in this diagram is actually the escarpment. Okay, so we can see the sudden change in the elevation in this area. Okay, so there is a sudden drop in the elevation, and the wall over here, the escarpment wall over here is almost 90 degrees okay, in angle compared to the horizontal over here. So it can be formed due to erosion as well as faulting. Okay, so just a gist of what is a fault is, if we consider this as a rock block, okay, without any kind of deformation, or this is like at time 0. Okay, so this is just a block of rock. It can be spanning a few hundreds of kilometers also. Then with time a kind of fracture develops. Okay, but the fracture is not exactly the fracture first develops only maybe on the surface, and slowly with either there is a pull on the rock from on these sides. Okay, so if there's a block, there's a fracture which is developed over there, and you kind of extend it or you kind of pull it away from each other. So what happens is, along this fracture there will be some deformation. Okay, so either the deformation, the fracture can extend to like downwards, either vertically, okay, either vertically or at an angle. Okay, so as per that, if we for example, if we consider that the rock block has deformed along this fracture, along this line, okay, and it has taken and like angular kind of a displacement has taken place. Okay, so this block over here, okay, this has moved downwards along this plane that has formed due to the displacement of the of this part of the rock, okay, along this plane, and this relative to this block, okay. So this is block A and this is block B. So the block A has moved, it appears to have moved upwards with respect to the block B. Okay, so this now is called a faulted rock block. Okay, and this area is actually called the fault plane. Fault plane, this line that we had seen, the where the fracture had originally developed, that is your fault line. Okay. So now when we like, obviously there has to be some nomenclature to generalize the such features, just such structural features in real life on the earth surface. So what we say is that if this is your fault plane, okay, so the wall, okay, or the foot or the rock block, sorry, so the block of the rock that is below the fault plane, okay, so that is called a foot wall, and the wall which appears to be hanging, okay, or which is on top of the fault plane is will be called a hanging wall. So when we are considering, there can be different types of faulting. Now for the current understanding, we are only dealing with normal faults. Okay, so for normal faults, your foot wall goes up and your hanging wall goes down relative to the fault plane. Okay. So now this fault plane can actually form this escarpments that we are talking about. Okay, so maybe this wall that we are seeing, okay, so this kind of the surface that is exposed over here in a vertical sense, like in a vertical section, this can be a fault plane. Okay, so that is why I try to explain the fault system and the some of the nomenclatures that are associated with a fault system. So you can have a foot wall. This could be the the block behind this surface can be your foot wall, and maybe the the river bed over here is actually the hanging wall. Okay, so escarpment is where your elevation changes suddenly, and yes, okay, and it can be the bottom of the cliff. It can be also the bottom of a cliff or a steep slope. Okay, and it can, as I said, it can also form due to erosion or or faulting. So maybe there was, if this is not a fault system that we are talking about, so maybe there is no footwall, there is no hanging wall. So what could be the other, you know, what could be the other cause of such a feature forming? So maybe this was kind of a gently sloping area. Okay, so gently sloping landscape was already present over here, and the water was flowing across or over this slope. But maybe with time, due to erosion, so there may be some kind of depressions that have formed over here. Okay, and with a sudden change in the rate of flow of the water over here, and maybe this area, okay, this part actually got disintegrated or it got eroded way faster compared to your lower regions. So what then could have been formed is that a different kind of slope change has already formed. So usually if there are no fault systems available or in such areas, Usually waterfalls, as we are seeing even in this example, can form due to just erosional processes also. It is not necessary for fault systems to be present in such areas. Escarpments can form due to both erosion as well as faulting processes. So, it's not always easy to view a topographic map. So, when we try to study geomorphology, maybe not going you if you are at a location, you cannot understand the entire extent of a geomorphic feature. Okay, so to understand the geomorphic, the different variations that we see in the geomorphology of an area over a very large extent of area, we need maps. So the maps that are used, for geomorphological studies are actually called topographic maps. So in topographic maps, it's easier for us to visualize as well as try to understand what kind of geomorphic features are present in an area. So suppose this is our topographic map. Okay, now we want to understand how escarpments could look on such topographic maps. So over here you can see these kind of wavy lines that we see, and if you look closely, this is not a very good resolution picture, but what we actually see in topographic maps are contour values. Okay, so contour values are actually give you the the continuous lines which join areas of equal elevations. Okay, so these kind of these almost parallel lines to each other, or these lines which you can see are actually some places they might even form concentric circles. So these are actually contour lines which give us information about the elevation of the area, and they join areas which have the same elevation values. So maybe this one has 15 meter or kilometer, whatever is the usually actually elevation is mentioned in meters only. So this might be a 15-meter contour line, okay, and this might be a 10-meter contour line, and then slowly we can see that the contour line may not be exactly parallel or similar to the previous or the higher or the lower contour line. This can be the 5-meter contour line. So at any place, as we had already tried to explain what is an escarpment. Escarpment is the area where you have the sudden change in the elevation. Okay, so if there is a sudden change in elevation, what we can assume is that the contour lines in those areas will have to be very closely spaced to each other, because if the distance between these two regions, okay, with different elevations is smaller compared to this area, okay, this is also 10 meters and this is also area of 5 meters, but as the distance increases we can see that the change in the elevation, the rate of it is very low. Okay, so it's a gently sloping area. But if there is a shorter distance between the two contour lines, so that means the elevation change has happened across a very small distance. So that means it is steeply sloping in that area. So for escarpment area, what we usually notice is such contour lines are very closely spaced to each other. Okay, so as you can see in this area you can see that the contour lines are very densely placed next to each other over here also and in these regions also. So this entire kind of feature that we see over here is actually part of an escarpment over here too. And as we had done in fluvial geomorphology, okay, so maybe these areas, if there is a river passing through this area, okay, so these can also be river terraces. So we also need to understand what kind of surface agents are also flowing, are present in this area. So this is actually the example of what I was saying when we were talking about the normal faults. Okay, so normal dip slip can also be called as the yes. Dip slip. What is a dip? I will just explain quickly. Is this okay? So if we are considering just this block of rock, and these are the different beds that are present over here. Okay, so this is bed A, bed B. What are beds? Actually, in sedimentary rocks, or actually, as we had said before, that earth itself is a layered structure. Even the earth's crust is made up of layers of different rocks. So the oldest rock is usually found at the bottom of a layer. If we are considering, if we are in a region where all the rock bodies that are present are actually horizontally deposited or horizontally formed. So A, B, C. So A would be the oldest, and C, if it is the topmost rock layer that is present over there, so this would be your youngest one. Okay, so this is where you have horizontal beds, and over here we can see that they are kind of at an angle, they are not exactly horizontal. So over here we can what would be a strike. Okay, so the strike is actually the imaginary horizontal line that you can draw on any feature. Okay, it can be a fault line, it can be a rock bed, anything. Okay, so it has to be a horizontal line, okay, which is matching the direction of the alignment of the feature that we are considering. So the beds over here, these are actually the strike line for all the beds. If we are considering the strike of this fault, so that is actually in this direction. Okay, so this is called the strike, and this is the strike direction. Strike is, it's an imaginary line, it is not physically present, but it is something we give to help us in interpreting the different kind of different kind of structural aspects of any of the geological features that we see. So if this is your strike, we can say that the bed is dipping, okay, with relation relative to the strike that we are seeing. So this is actually the dip angle of this bed. Okay. Similarly, if this is your strike of the fault, then if we kind of draw a line which is 90 degrees perpendicular to the strike line, and the direction of the direction of the inclination of the feature. Okay, so we cannot draw a line perpendicular to this strike line, okay, if you extend the strike line, but you just draw a perpendicular line straight downwards, but this does not give you the information about the depth of the fault plane over here. So we have to draw it perpendicular to the strike line, but along the inclination of the feature that we are trying to find out. The strike and the dip angle is an amount. Also we can also have the dip direction. So this is the direction of the dip, and this is the strike direction, okay, and this kind of the angle from the imaginary plane that is cutting the strike, and the plane that is that we are considering along the dip direction of the feature. So that angle will give you the dip angle. Okay, so if I kind of draw it over here, so this is your strike and this is your dip. Okay, so this is your dip direction, and this. Okay, if you consider a plane over here, so the angle between the planes, okay, so the vertical angle between the planes would be your dip angle. So, in actually in this subject we are not going very deep into these different structural aspects and features and characteristics, but usually in structural geology there is a subject. So, in that these things are very um, well established and well explained, but for now to understand, when we call normal fault is that usually the as we said, this is the hanging wall block and this is the footwall block. So, the hanging wall block is usually moving in the direction of the the dip, okay, and the entire displacement is just along the dip of the fault plane. So, that is why we call it the normal fault, and as I said before also, the hanging wall moves down relative to the fault plane as well as the footwall that is present over there. So, this is actually this area, okay, if suppose this area is depicted in this topographic map that we have been discussing about. So, the elevation changes over here is very quick. Okay, so very it's sudden, it's at a rapid rate, okay, and it is across a very small distance, the elevation change that we see. So, hence we can consider this area as an escarpment if it occurs along a large stretch of the area. Now, we will move on to other geomorphic features. Okay, so now we were when we were talking about escarpments, so mostly erosional or faulting. Erosional, obviously it can be due to any of the surface agent processes. But when we are talking about escarpment created by faulting or near fault systems, so that is totally tectonic tectonics controlled feature that is formed. So, now we will come to features that have both tectonics and erosional processes playing a combined role in their formation. So, the first we will try to see what happens when you have surface running water that is moving downhill, and also considering a change in the tectonic setup over there, either due to uplift or kind of subsidence that we see. So, in this example we can see that this area is getting uplifted, okay. So, this again you can try to see that if if I simplify this diagram, this is your fault plane, okay, and this part is moving up and this part is moving down. So, this is your hanging wall and this is your footwall, this is your fault plane that we see over here, okay. This is your fault plane. So, this is a type of or you can easily understand it like a normal fault system that is present, okay, and the rivers are flowing over here. These are three different drainage basins that are there, and these raised uh, boundaries of the drainage basin are called drainage divides. We had already seen this in the fluvial geomorphology part, okay. So, what we see is between the two drainage basins over here, okay, along this drainage divide that has formed, we see kind of triangular shaped features that are formed along that exposed surface. It can be, it might have been an escarpment, okay, or it is a fault plane right now. So, we can see that they formed facets. They are triangular to poly, it can be triangular, it can be polyhedral, depending on whether the drainage divide are divides are actually, they have already met each other, or they have, they are still a bit, spaced from each other. So, hill slopes that lie between two adjacent drainages along a mountain front escarpment. So, these escarpments that we are talking about over here, these are mountain front escarpments. So, it usually, foothills or a bit or at a, level which is slightly above the foothill areas in the mountainous regions. Okay. So, the triangular facets that are created, it is due to a combination of your uplift or extension. If we are only considering uplift, okay, that only this area is going, you know, rising above the main sea level, relative to the main sea level, or there is a faulting system that has, that is present over there, and the changes or the, uplift is happening due to the extension of the area over there, which is causing the occurrence of normal faulting in this region. So, so it's a combination of such uplift or extension along with the erosion that is happening due to the drainage, river drainage basins that are present over there. Just excuse me one moment. Okay. So, as I already explained, these are usually the effects of normal faulting processes. Sometimes, thrust faults are also, associated with these. I will explain it later on how what are thrust faults and how these kind of facets can occur in those areas also. And okay, so these are usually seen in faulting, faulted areas, as well as they can be effects of the erosional processes of the drainage basins that are appearing or that are occurring over there. Okay, on the footwall surface, as I said, this is your footwall. So, when we are talking about normal faulting, so this is the footwall, surface that is seen over here, and these facets are forming on this footwall surface that is exposed during normal faulting. Okay, so this area is getting eroded. So, these are and then these are actually bounded by the different main river channels that are flowing down from the higher elevated regions. So, how do we understand the kind of tectonic processes that are happening, which are forming these triangular facets, and how does it help us in understanding whether the tectonics that are occurring in this region is active or inactive, or what is the rate of the tectonic processes and erosional processes that are happening over here. So, we can have a comparative study. So, if there are large facets, okay, so this triangular faces, if they are large in size, then it can happen due to frequent faulting, okay, and if there is frequent faulting processes that are happening, and that is causing the that is forming these facets, okay. So, if it is high in frequency, if their occurrence is much frequent, then it can be called as a tectonically active front. And then what we say that the fronts are less dissected. So, the dissected as in that these occur at kind of spaced out. If the facets are very large, okay, then, and the mountain front is only this much in area, okay. If these are very large, then the mountain front is not very it is not dissected by a large number of outlets that are present over here, and most of the the development of these facets are mostly due to the faulting processes. So, that is the tectonic processes. But if we have smaller facets, okay, so then it is actually less tectonically active fronts, Okay, so there is not much uplift, so there is not much of the escarpment surface area that is available for the facets to form in a larger size. And there are more dissected fronts. Why? Because if that area is stable, okay, so it gives the time for the drainage, the smaller streams in the drainage basin to actually reach out to to farther extents, and they themselves might create smaller drainage basins, and which might be flowing which might be kind of incising the mountain front that is there. Okay, so more development of more drainages happen across the front when it is a tectonically inactive area, and since it is less tectonically active fronts, we will see smaller sized facets. We can find it in this example over here. Okay, so this is your mountain front surface, this entire surface. Okay, so by here when we see that these are large facets, so not much of the mountain front range is being incised or by the different drainage basins over here, because the rate of uplift is also very uh, you can say this actually depends on the size of the drainage basins. The drainage basins are pretty large in size, okay, and accordingly we can see that the facets dividing the drainage basins are also larger in size. And then over here, if the slope changes, okay, over here as we see that the slope is changing, okay, and the erosional processes that we see over here is being more active in this area. So we have the more number of smaller triangular facets are seen over here. Okay, so when the drainage density increases, the height of these ridges is lowered, and smaller triangular facets are being formed over here, and more small alluvial fans can also form in such foothills of such areas. So this is how the if the how the erosional processes or the uplifting processes that we see in the mountainous regions can form such geomorphic features, these facets, and these can help us in understanding the rate of the processes that are occurring over there, and what is the kind of frequency of these processes that are occurring in these regions. This is an experiment where they try to create faulted systems, and also they try to see if you let water flow on this kind the sediments, what sort of features do form when you kind of when you have faulted that area, or you have raised one portion of the landscape, you have uplifted one portion of the landscape. So you can see over here these facets are formed over here. Okay, these facets are forming, and these channels are incising this fault front. Okay, so this is the side view, and this is the uh, parallel to the fault surface. This is your fault surface. Okay, so from the front of the experimental area, you can see that these are the facets that are forming. Okay, so over here you have a small facet, and over here again a large facet, and these are the kind of the streams that are flowing down, and these are the drainage divides, okay, so that are forming over here due to the water that is running over the surface of this the sedimented area. So as we these are kind of observational features that we have seen till now, like you observe these things either in on topographic maps, or when you are on field that you see, but to quantitatively trying to understand uh, the tectonic control of, on formation of such geomorphic features. uh, a lot of studies have been done previously, and a lot of authors have come up with different kind of indices to quantify such processes, like whether you will like according to a certain indice we can see whether it is more tectonically active region or tectonically inactive region, or we can say that this area is controlled mostly by tectonic processes or erosional processes. So one of those geomorphic indices is the mountain front sinuosity index. So over here in this diagram, if you see, the LMF, okay, stands for the sinuous distance. Suppose we are only considering the mountain front between these two only within this region. So LMF is actually this entire length of the mountain front that we are trying to study, and LS is the straight line length, that is that we take from one point to the other point of the mountain front that we are trying to study. So that gives us the SMF index, okay, mountain front sinuosity index. So why we use it? So we try to understand what kind of tectonic activity is taking place in such mountain fronts. So we try to see what is the what kind of index value will give you the understanding of whether your tectonic activity is more prominent in this region or it is the erosional one. So if you have low SMF values, we have more active fault segments. Okay, so more tectonically active regions will have low SMF values, and if the SMF values are higher, that those areas are actually controlled by erosional processes more predominantly compared to the tectonic processes. Okay, so this how that is kind of related to this is, if your LMF is higher, okay, so LMF is that this appears to be more sinuous in kind of feature. So there are more the sinuosity, or you can see so this is actually governed by the erosional processes, but the less sinuous this region is, okay, so if you have this is your high LMF, and if your LMF is low, that means the it's not that irregular in nature, it is close to the value of your straight line length for the mountain front itself. So this is mostly erosional. The causes of such a mountain front would be erosional dominantly, and of such less sinuous nature of the mountain front is actually due to your tectonics. So judging by how how the mountain front is varying in its sinuous nature can give us an understanding whether this area is tectonically active, or the processes which are actually changing the landscape of the mountain front over there is actually governed by erosional processes more compared to your tectonics. Okay. So now as we can see that we are talking about active tectonics. So what are active tectonics? So active tectonics usually concerns with the different tectonic processes that are occurring at the present day. a lot of features we find or we try to study, they are not part of the active tectonics. So, they had been formed because of some major tectonic processes in the past. Okay, so they do give us an understanding of how some area was formed in the geological past. But to understand the entire kind of the variations that we see, we need to understand, we need to study the active tectonics too, not just the past tectonics but the active ones that are happening right now. So, what it has observed, as we had looked at in the first I think first live session, I had given the principle of uniformitarianism. Okay, so according to that, whatever processes have occurred in the past, the same processes are occurring in the present day. So, if you study the processes that are occurring in the present day, we can view into the processes that had happened in the past, and so that helps us in kind of bridging the gap that we have in the scientific gaps that we see while trying to understand what happened in the past and what is happening right now. So, studying active tectonics is important, especially in areas which are very much prone to natural hazards. Okay, so why? Because mostly any kind of plate motions that we had studied or that we had looked into the I think the second live session, the second week live session where we were talking about divergent plate boundaries, convergent plate boundaries. So, in that we had seen the different kind of plate motions that happen. Now, these plate motions are obviously not random. Okay, so if some place where you have the divergent plate boundary, okay, so where it is kind of extending from one plate, it is extending. Okay, so it is getting pulled apart. So obviously the area over there is not totally just breaking away from each other. Okay, so at that area there needs to be some material that is deposited, or the the kind of uh, the land over there. Okay, so the land portion over there, it cannot just break off. Okay, so there is some tensile characteristic of the material over there, so that has to be accommodated by some other kind of a future. So when we talk about divergent plate boundaries, so it is not just like a break between the two plates. Okay, so this area, this kind of space that is being created due to this deformation, it is accommodated by different kind of features as well as processes. So, what those features could be? They can be faults, there could be occurrences of earthquakes, and different kind of structures that can be seen at the plate boundaries or inside the intra-plate region also. So, all these formation of such structures are actually associated with active tectonics, and hence it is important for us to understand these processes as well as the rheological properties of the material that are part of these processes. So, the rocks that are forming over there, or the rocks that are getting destructed in the convergent plate boundaries, where are they going? Are they replenished, or they cannot be totally lost to us? So, they are converted from one form to another form. Okay. So, all these are part of active tectonics. We know that these are still happening right now, and if we study these and try to understand these active tectonics, it can give us a way to look into the past of landforms, landscapes and features that are geological features that have already formed. So, even active tectonics can be classified as per their timing with respect to the geological time scale that was shown to you, I think, in the early on live sessions. So you can have neotectonics, so that are part of the Neogene and Quaternary time, the geological time scale. You have these epochs and periods. So Neogene, Quaternary tectonism. Then you have young tectonics. So that happened in uh, in the late Pleistocene and Holocene time. Okay, so these are some tens of thousands years. Okay, and then you have the recent tectonism. So this is the youngest form of active tectonics that we see, where we have seen in the last few thousands of years alone, or the upper Holocene part. Okay, so these are some of the time frames that we consider when we are talking about active tectonics. So how do you uh, distinguish from, or how do you point out that this area is actually undergoing active tectonics? So these can be a combination of topographical changes, as well as most importantly geomorphic changes that we see. So the development of meanders. Okay, active tectonics may not occur, uh, they may occur at large extent of areas, but sometimes we consider the features that are forming at local scales. Local scales is few hundreds of kilometers. Okay, maybe we try to understand the active tectonics only in that. So for example, Himalayas, they range for hundreds of kilometers. Now every area, okay, so when we are trying to understand the active tectonism, every small local area of Himalayas have different kind of a response to the deep tectonic processes that are happening over there. Okay, so when we try to see the active tectonics, we take a few tens of kilometers, hundreds of kilometers, and we try to see what kind of geomorphic features are being developed in those regions. So we can try to study the local development of meanders. We can try to see the braiding pattern of the rivers that are flowing over there, and this are if we are considering the action of fluvial agents. Okay, so mostly as I am saying that in active tectonic regions are usually seen in the mountainous regions, mountain building regions. Okay, and hence we are considering or focusing more on the fluvial parts or the fluvial processes, and also because we have already done the fluvial processes part, so it is easier for us to correlate and try to understand the correlation it has with active tectonics. So you have local development of meanders, braided patterns, the channels or the valleys, whether they are narrowing or they are broadening, and local development of smaller water bodies like ponds. So all these all these features, when you try to understand the rate of their formation and also their shapes and the different any kind of quantitative analysis that we can perform over these features, that can give you an understanding of whether this area is active, like the tectonics in this region is active or not active, or the what is the rate of the occurrences of the tectonic processes that are forming these. So as I had said that now it's important for us to understand the different kind of fault systems that are uh, that are actually parts, very basic parts to understand the different plate boundaries itself. As we had seen in the considering plate boundaries, which are thousands of kilometers in size and spanning the entire surface of the earth. So you have divergent, convergent, and transform. So all these boundaries and the actions that are seen at these boundaries can also be visualized at local levels. So, the extension and the compression, extension when we are talking about the divergent boundaries, the compression action that we see in the convergent boundaries. I think I made a mistake. So, the extension that we see in the divergent boundaries and the compression that we see in the convergent boundaries and the kind of the lateral kind of motions that we have seen in the transform boundaries. Okay, so all these can be visualized at local levels if we are trying to consider just one small one few tens or hundreds of kilometer areas also. So, these same processes or the same kind of directional processes, if we try to apply them at local levels at smaller scales, we can try to understand the fault systems that are created by these extensional or compressional or transitional the translational kind of motions that we see. So, the first one that we will try to see that can be correlated with your divergent kind of actions is the normal fault. I had already explained the normal fault. Okay, so the formation of normal faults is usually when the forces that are acting on the on the rock block or uh, the area that we are studying. So, the forces are pulling away from each other. Okay. So, what happens is if there is a zone of weakness that had formed in that area, so the rock over there will be displaced, okay, and it will be deformed due to this force, okay, this extensional force. So, normal faults are usually formed due to extensional forces, and due to that you have the normal fault forming where your hanging wall block relatively moves down, okay, and the footwall block appears to have moved upwards when you are considering the inclined fault plane. Now we come to reverse. Okay, so reverse you can have you can try to understand by saying that along the fault plane that we see, the hanging wall appears to have moved above, okay, moved upwards with respect to the fault plane that is present, and the foot wall moves downwards with respect to the fault plane. So, you can see how it is the direction of the movement of the blocks is opposite, okay, in normal and reverse. So, this usually happens when the forces that are acting on such areas is kind of compressive in nature. So, the rock block, the two sides of the block are actually getting pushed towards each other, and due to that, okay, so due to that forces or the fractures or the discontinuities or weak zones that are formed due to that helps in such kind of directional deformation. So, this is due to compressional forces. Now, to understand why you for extensional forces they will be moving the hanging wall moves down and the foot wall moves up. So, these are actually due to the kind of the rheological characteristics that are there due to the different kind of stress that is put on such rocks. So, that is a different kind of aspect that we learn when we learn these structural features in depth. For now, you just have to remember that for extensional forces you have normal faults. For areas which are undergoing compressional forces you have reverse faults forming. Now, there are different kinds of uh, there is a different kind of normal fault and reverse fault. when the fault plane, okay, when the angle of fault plane changes. So if the angle, so what angle are we talking about? The angle this plane is making with the vertical, okay. So this angle, so over here this angle is, you know, much lower, or you can, you know, if we try to consider with the horizontal, we were talking about the strike, okay. So if this is the strike plane, and this is the you know, this is the strike plane of this fault. So the angle that this fault plane is making with the strike plane, this is called the dip, okay. So over here this dip is you know, it varies from say 30 to 45 degrees, okay. But if this angle is lower, it's much lower actually, over here it is you know, kind of saying less than 45 degrees. It usually is less than, you know, sometimes it can be less than 30 degrees also. So this is still a normal fault, but this is a low angle normal dip slip fault, okay. And similarly when the angle, okay, so the dip angle of the fault plane you know, associated with the reverse fault is much you know, smaller, you know, less than 45 degrees or less than 30 degrees, those are called thrust faults. This is important for us to know, the thrust faults, because we will see later on that the some of the examples where we try to understand active tectonics, thrust faults are important features that are present over there. And then you have, you know, different kind of these are associated with the translational kind of forces. So these are, you know, moving along each other or moving along the fault plane, okay. So they are not moving downwards or upwards, so they are moving in the horizontal kind of directions, but they are moving, you know, either away from each other or, you know, or in the opposite direction. So so you can see over here, so this is called a left lateral. Why is it called left lateral? So if you are facing the fault plane, okay, so this is the fault plane and you are facing the fault plane, okay. So if you see that your left side block is moving, okay, so that is your left lateral, and if you see your right side block is moving, then it is a right lateral. You can also you know, kind of observe this even if you are not facing the fault plane, but you are, you know, kind of standing and you know, standing over here. So if you are standing over here, so you can see that the left block is appearing to be moving towards you, okay. If you are standing here, you will see that the right block is moving towards you. So even then you can call it you know, you can classify it as either left lateral or right lateral. And then you can see that this one over here is a combination of the normal fault and the you know, the the lateral faults that we are talking about, okay. So you see that there is movement along the dip of the fault plane also, as well as, you know, in the strike direction of the fault plane also. So this is called a normal left lateral fault because it's the left you know, kind of the left block which is moving in the you know, towards you along the direction of the strike. So any left lateral fault alone can also be called a strike slip, because as we said, you know, this is the strike of the fault plane, and if the movement of the blocks is only along the strike direction, either, you know, towards each other, towards yourself, okay. So whether the right block is moving along the strike towards each other, or the left one or the right one is moving towards each other only along the strike direction of the fault plane, it can be called a strike slip fault. How we had the dip slip fault over here. So when you have a combination of both strike slip and dip slip fault, so you can kind of name them according to the kind of appearance that we see. Appearance how? Since the footwall over here still appears to be moving upwards, with respect to the fall plane, and the hanging wall appears to be moving downwards with respect to the fall plane. It is called a normal fault, and the direction of the block in the strike direction, whether it which block is appearing to be coming towards you, you can then name it according to the direction and the left lateral fault. Okay. So over here we can see that we can also have the reverse lateral fault. Why? Because the hanging wall has moved upwards, okay, and the foot wall has moved downwards, as well as you can see over here that over here the left block is moving towards the observer over here. If you are standing, or if you are facing the fall plane, you can see the left block. Okay, so the direction of the movement is it's towards the left side of the observer. So hence this is a reverse fault and it is a left lateral fault. So this is how you can classify different kinds of fault systems that we see. It can be just one type of fault system, or it can be a combination of two types of fault systems also. And most of the active tectonic regions, they will have either combination of these different faults, or they can belong to one single fault system too. So over here, as we were talking about the different kind of facets, the triangular facets that we were seeing. Okay, so we can see that at different fault setting how the triangular facets can form. When we have the thrust faulting, okay, so that means the fault plane, okay, is in this direction, and we can see that the hanging wall is actually moving upwards and the foot wall is either not moving at all, or it appears to be moving downwards. Okay, so this is an active reverse fault. You can see how the facets are smaller in nature. Okay, and these are actually deposits that are the deposits that are done by the erosion of the facets themselves. Okay, so these facets are smaller in in sizes. For normal fall setting, you can see that you have larger facet over here. Okay, the triangular facets are more prominent and very nicely developed in normal fall setting. For strike slip faults, since the fault plane is not at all exposed, so there is no kind of development of fault scarps or the facets that are formed due to the change in the elevation, or change due to the tectonic uplift that is present over here. So there is only lateral movement of these areas. So this is moving in this direction. So over here, but we see that there is a diversion that we see in the stream directions over here. Okay, so according to the movement, so as we can see that this is actually a right lateral strike slip fault. Okay, why right lateral? Because if you are an observer facing the perpendicular to the fault plane that is there, you can see that the right block is actually moving towards you. So hence this is the right lateral fault, and you can see that the reverse the streams actually change the direction, or there is a slight change in the the flow direction of the rivers over here. So these are some of the features that we can kind of observe when we are studying active faults in any region. So due to these uplift and subsidence, okay, so you can have the fluvial patterns that we had studied, okay, they can also change due to the occurrences of the faults in this area, okay, and due to the occurrence of the faults you can have uplift at the region, or subsidence in a region, and as per the changes in the slopes and the slope, the rate of the change in the slope as well as the rate of the flow that changes due to that, they all of them together can change the channel patterns that we observe in this region. So you can have variation in water discharge or sediment load, and if you have an uplift, the bedrock, okay, the solid rock which was not weathered by the river previously can be exposed, and they can cause a barrier to the flow of the river, and then the river will change its speed, direction, a lot of roles are changed because of that. Then obviously human influences, and most importantly for this part, tectonic influences. So all of these play a role in the development of different channel patterns. We had done,
Ma'am,
yes,
please one repeat it once again.
repeat what exactly?
Ma'am, last page.
This one. uh,
मैम इसके पहले का. Yes, ma'am.
हाँ, तो ये एक्चुअली हम आगे समझेंगे. सो just an example, you can see in this diagram over here the stability, or the patterns that we see in the channels. Okay, so this is a straight channel, this is also a straight channel, but we can see kind of sediments being deposited along the banks of the channel, and then you have a meandering channel. So all of these are actually controlled, okay, by the amount of sediments that it is carrying, the sediment size that is being carried by the river, as well as the stream power and the flow velocity. So that is what I have explained in these points, that the channels, the river channels, can show variations in the channel patterns related to the amount of water that is being carried by the river, amount of sediments that are carried by the river, the presence of bedrock. So presence of bedrock, as in over time what happens is the bedrock, or the rock that is present at the channel bed. Okay, so over time it gets eroded, but maybe due to the uplift that is happening. Suppose if there normal faulting occurs, and the stream is overflowing the footwall block, which has which appears to have moved upwards. So what happens, the bedrock now is exposed, and due to that the river now has to change its direction, or it has to change its kind of the rate of flow, or the energy that is required for it to cut through that bedrock. So those are important to understand the different kind of channel patterns that are developed due to the changes because of this. So human influences, obviously if you create a dam, you are going to minimize the rate of flow of the water, and also you are going to kind of the sediment, the amount of sediments that are being carried is also not as much as it would have been if there was no dam over there. And obviously tectonic influences, as I said, if there is faulting happening, as we even saw that due to the strike slip kind of strike slip kind of movement can cause the stream to change its direction, or if there is the escarpment that we had seen, if there is a sudden change in the elevation, it will have to try to accommodate that by changing its pattern. So it can move with the least amount of resistance that it can have. So this is what I meant, that the different kind of fluvial patterns that we will see due to the action of erosion, deposition, as well as the tectonic processes.
Yes, ma'am. Thank you.
Yeah. So in fluvial geomorphology, we had studied one of the indices, okay, kind of geomorphic indices, that was the sinuosity ratio. So what is a sinuosity ratio? Is that, suppose this is your river channel that you want to understand the sinuosity, the ratio of this you want to calculate. So you calculate the entire length of the stream channel. Okay, so this length of the stream channel is this dotted line, and the straight line distance between the ends of the channel reach that you're trying to calculate. So that gives you understanding of the sinuosity of the channel of the of the part of the river channel that you want to understand. So if your length of stream channel increases, your sinuosity increases. Okay, so the way that the river channel changes its sinuous pattern or changes its sinuous nature can can be controlled by the change in the slope of that area. So over here, this is also part of the it was studied by Shum, and who gave these these different kind of channel patterns. So they tried to plot it for a river channel that they were studying, that lower sinuosity values are given to straight channels. That is obviously understood that close to 1, that means the length of the stream channel and the straight line distance, if they are close to each other, so you will have a lower sinuosity ratio, so they will be showing straight kind of nature. But with increase in slope, as we see that the sinuosity increases. So if the straight channel is flowing, and then it changes into the meandering pattern when there is a change in the slope, okay, and then you will find that sinuosity again decreases when we have a braided kind of a pattern at higher slope percentage areas. So you can see the same thing over here. Okay, so it starts off with 1, then it can change to 2, then 3a, then 3b, and then with time it actually becomes more braided in nature, braided and anastomizing. Okay, so this is what the tectonics, how they will have a so a meandering stream can change back to a straight stream. Okay, if there is a change in the tectonic setup of that region, a braided river can change back to a meandering stream if there is a change in the slope due to the tectonics that are happening over there. So this gives us a relation that the fluvial patterns are controlled by the tectonic processes that are taking place in such regions. So there are two kind of processes that are associated with the fluvial pattern changes that we observe due to tectonics. So that is aggradation and degradation. Aggradation means that aggradation, you can in layman terms you can see anything that is builded upon, okay, and degradation is something that is lost. So aggradation and degradation can have changes in the base level of the river, okay, and it can also mean that the amount of sediment is more. So the deposition, all the depositional processes are associated with degradation, and the erosional processes would be associated with the degradation. Okay, and for aggradation, for deposition to occur, you will have lower kinetic energy of the water that is flowing. For degradation, that is loss of the sediments or more erosional processes, for it to happen will have more kinetic energy. Okay, when we are concerned with the fluvial river channels that we see. So you can see this table, like the factors that we are trying to consider, and the different kind of variations we see if you have aggradation happening or degradation. Now, to understand that as an example of the active tectonics, so if you have suppose this was the original kind of elevation level, okay, across which the river was flowing, that you can see even in the dashed line over here. Now, due to this uplift, okay, in this area over here, sorry, yeah, so the uplift is happening in the region 2 and 3, okay. So there is a slope change over there here, and there is again a slope change over here. So the processes that are active will change, okay. So since this area is lower in elevation compared to this area, aggradation is going to happen, and since this area has got uplifted, the river to try to maintain this profile that it had created at first before the tectonic changes had happened, it will try to go back to that stage. So what it will do is that it will try to degrade this area, okay. So this area, this dome, it will try to erode it out, and whatever erosion is happening over here, now again since over here the slope change is again gone lower than the previous stage that was there, it will try to build it up, so you will have aggradation. So this is for an example of a dome kind of tectonic feature that is being created. Now if you have a fault, okay, so before the faulting happened, this dotted line, this dash line, sorry, is actually showing the the equilibrium kind of stage that was reached by the channel. Now since the tectonic disturbance happened, this is the footwall, it has gone above, and the and the hanging wall has moved lower, moved downwards, okay. So this is a normal fault example. So since this area has gone up, so the region above the previous profile or previous stage that the river was flowing in, so it will try to degrade this area, and the due to degradation, the erosional processes and also the change in the slope in this area, the material is going to get deposited over here, and there will be aggradation in this area, okay. So this is how uh, the kind of depositional and erosional processes try to balance or try to accommodate the tectonic variations or tectonic disturbances that they encounter, okay, when the river channel is flowing across an area. Similarly, if you have this area, this there is an anticlinal uplift, the doming kind of effect that we see, the channel patterns change okay, due to that. So that means the river, this is like from the top view, okay. So this area is actually got uplifted. So what happens is, this area, since it is at a lower elevation, okay, so this place we will have aggradation, and aggradation area is mostly associated with anastomizing channels, okay. And then over here there is an uplift and there will be degradation. So during degradation you will mostly see straighter channels, okay. And later on when it tries to reach at later half, it will try to regain its meandering pattern. So it changes with the changes in the tectonic phases that are happening over there. Similarly, if this area has gone down, okay, so like if from top you are looking and this region has gone down, okay, so from this meandering kind of a pattern, it will try to the left part, okay, so it will try to first make an anastomizing channel where the subsidence has happened. Okay, then from that anastomizing you can have, you know, as the elevation changes again, it has gone on top, it will try to degrade the area over there, you will have a straight channel. So this is how changes due to the active tectonics that is happening can be seen in the channel patterns also. So the sinuosity increases when there is increased slope, and the sinuosity decreases when there is decrease in slope. Okay.
Ma'am, explain it once again.
Okay.
ये
So
बस समझ में नहीं आया जो पहला आपने बताया
हाँ हाँ
एंटीक्लाइनल अपील.
हाँ एंटीक्लाइनल अपलिफ्ट तो ये वाला जो है, okay, this doming kind of effect that we will see. Okay, so the dome, uh, the area is uplifted, okay, and due to the change in the slope, the channel patterns will change. So channel patterns will change as in the sinuosity. Okay, so we are trying to understand the sinuous nature of the channels that are flowing. Okay, so if the slope is increasing, okay, sinuosity increasing. So over here we can see, like, this is exactly, you know, kind of uh, if you see parallelly, okay, with time what is going to happen is that the slope is increasing over here. Okay, so as the this region, okay, this is going down. So what is happening, you have aggradation. When we have aggradation, you have more deposition, and if you have more deposition, more point bars kind of features will form, and you will have anastomizing river. Okay, so now, and when you have, you know, kind of a uplift that has happened, now to degrade that uplift, okay, it wants to come down to that level where it has you know, kind of the profile that was there previously. So as I said, the meandering river, okay, so the meandering river can change into anatomizing river as well as straight rivers. Okay, so from here when you have uplift, okay, so the slope is increasing, over here the sinuosity is increasing. Okay, so from anatomizing it is going to a meandering kind of a phase, so the sinuosity has increased. So that's what I meant. Now with this inclinal subsidence, so the region is going down, okay, your slope is changing, then again from sinuous nature, okay, from sinuous nature it is going to go towards lower sinuosity, lower sinus pattern. So this is how, you know, with tectonics and the increase and the decrease of the erosional processes and the depositional processes, the channel patterns also change. So as over here, so increase in sinuosity, okay, so this area is actually accompanied with the slope changes. So straight river can go into meandering, meandering river can go back into the anastomizing kind of a feature. So that is what is being explained in this area.
Yes, ma'am.
Okay, now as we said, so over here if we are, you know, kind of seeing the tectonics where there is uplift over here, and this is the profile. So what will happen over here is aggradation, then over here you have degradation, and you have aggradation again. So as you see, the kind of, you know, for depositional features are also changing over here. Okay, so you have more bars in aggradation areas, okay, but in degradation area you have bars but as well as terraces. So terraces are usually you know, mostly erosional kind of you know, areas, or where the changes in the kind of the you know, base level of the river channel happens. So that is what happens over here when it tries to you know, accommodate this change in the topography that we see. Then again in the aggradation part you can see that the sinuosity has, you know, kind of decreased, and over here you can see that it is mostly a bar braided, or it is again going closer to the anastomizing channel pattern. And in the subsidence part you can see that degradation happens here, aggradation happens here, and degradation will happen here. Okay, so as for that you can see how the depositional features are changing. So sinuosity is another index another index, geomorphic index, that can help us in understanding the tectonic controls in a region. The another one is stream length gradient. So how the the stream is changing. Okay, so the gradient of the slope and the how the changes in the local slope actually is a control. It's controlled by the tectonic processes, can be determined by calculating stream length gradient at different sections of this river channel that we are seeing. So consider this segment. Okay, this is the midpoint of the segment. So this del H, okay, so this 50-meter is the elevation of this area, and this area, and this area the elevation is 25. So the formula over here calls for the DH, that is the difference in the elevation, as well as the difference in the or you actually say the kind of the distance between the two points of the section of the river channel that we are trying to study. Okay, so this is del L, and L is the distance from the midpoint of this channel segment to the drainage divide. So that this gives us the stream length gradient index. Now over here we can see that SL is kind of proportional to the local slope. Okay, the DH by DL is actually the local slope. So changes in the local slope will have a control over the stream length gradient index. So what we see is that for the higher values, if your stream length gradient is higher in value, uh, that means the local slope is also it's higher in that in that sense, and the streams are trying to flow through actively uplifting regions. Okay, active, so the local slope is changing very rapidly, and the or it is very difficult for the stream to kind of accommodate the kind of geology that is present over there. And for lower SL values, we have seen that this stream is actually trying to flow in tectonically inactive regions, or slowly uplifting regions, and the resistance of the underlying rocks is much lesser, and it is actually overflowing softer rocks. Softer rocks, it can be um, sediments, soft sediments, or sedimentary rocks which are easy to erode by the action of the running water. Then another geomorphic index that we have is the valley floor width to valley height ratio. So how the valley width is changing with respect to the valley height, that can tell you what sort of upliftment is happening, what is the rate of the upliftment that is happening. So that is again the this index VF is proportional to the valley width. Okay, so if you have wider valleys, okay, so that means the width is much greater, so you have high VF values also. Okay, so what that means is that the rate of uplift is low. Okay, so it since the rate of uplift is low, so it can easily form wide bottom, or flat bottomed valleys. If your VF is lower, that means that it is causing or it is creating V-shaped valleys because the elevation change is happening so quickly that the river channel is just cutting through and trying to accommodate the elevational changes that are happening. So V-shaped valleys will have low VF values and they are indicative of active tectonic active uplifting processes, whereas broad U-shaped valleys have high VF values and mostly they are created by lateral erosion, and if there is more lateral erosion, that means the slope change is not very evident, that area is tectonically more stable, all the tectonic processes are not that active and happening at a very slow rate. So as we were saying that the channel respond to the tectonic deformation. So we will try to see how the deflection or the variations are related to the shifts in the kind of the stream power that is there. So if this is your profile and you have uplift over here and for the faulting process over here, okay, so you will have as per the aggradation, okay, then you have degradation, and then you have aggradation again, then you have degradation again and aggradation. So you can see how the response of the channel is going to vary along this profile. So there is going to be there is going to be deflection in the direction of the stream also. So at the zone of uplift, there is going to be some deflection from the normal kind of the direction of the flow. And then again over here where you have the faulting that is happening, since the flow direction is now in this manner, it tries to go back to its original form. You can see due to this, then there is another deflection over here, and then there is zone of subsidence. So usually in zone of subsidence, the river the channel does not cannot deflect much, okay. So zone of subsidence, mostly you have aggradation that is happening, okay. And similarly if you see how the channel pattern is again varying, we had discussed this, okay. So when you see in this area you have the meandering river that is happening now due to the uplift over here, okay. So over here you are going to have some part of the aggradation that is happening over here, okay. And the channel pattern from meandering, it has gone into the braided kind of pattern. Then again when there is stability in the slope change over here, like there is no slope change, so again it tries to go back to the meandering form, but again there is a tectonic disturbance over here and the faulting, and we can see here again the channel pattern has changed. Similarly, if there is a kind of straight river that is flowing, so low sinuosity, but as soon as it interacts with the uplifted area, it changes into a meandering kind of a pattern, okay. Then again it reaches another tectonic disturbance disturbed area, and then again you can see that it has a high sinuosity because there is a change in the slope over here. But as soon as it goes into a more stable region, it will try to go back to the low sinus kind of a pattern. So these are again some examples, like if you change your starting stream, and you can see how it changes. Similarly, you can see this is an example of how the Satluj river, okay, how the pattern and how the direction of its flow has changed. So the grey one is the previous one, 1975 river channel, but in 2005 you can see that there is much lateral change and also changes in the direction of its kind of the flow over here. So the channel configuration changes with time, okay. So downstream, so this area is actually the downstream, so there is due to the differences in the elevation of the area and due to active tectonics that are happening over here, the channel pattern has changed over here. Sometimes if like these things you are talking about in the mountainous regions. So, but slope variations can happen even in the floodplain areas. Okay, so in floodplain areas, you can, if there is a tilt, okay, you can see the slope over here is tilting in this region. So we can see that the presently the channel is flowing in this region. Okay, but these features that we see over here, okay, meandrium mosaics and more cut off meanders that have been cut off previously because the channel has shifted from uplifted areas to the down tilted areas. So these features can give us an idea about how the tectonics had changed, like this area got uplifted, this area was subsided. Okay, so even these lateral kind of shifts in the meandering can help us in understanding the tectonics that are active in this region. So you can see you have asymmetric rifting is one way how this can happen. Okay, and we will see another example called piggyback basins. Over there also we will see that the channels can shift from uplifted areas to down tilted areas. You can see that there is a migration of this channel from the uplifted area to the downgoing area. So this can be either just upliftment as we see in like fold mountains as we saw the doming, or it can be due to the creation of faults. Okay, so this part has gone up and this part has gone down. So these kind of small features that we see, these are all defunct meander loops. Okay, so these have been used to be maybe oxbow lakes also, and sometimes we find traces of these channels over here. Okay, so this might have been the kind of area where the channel was flowing previously. So these can be called as paleo channels. So these paleo channels are actually on ground, they are characterized by these features. So this is kind of like a gist of the different geomorphic indices. So we did mountain front sinuosity, valley floor, okay, and the stream length gradient also. The other ones are also used, but for ease of understanding, only 3 of them have been covered here. Now we go to active faults. Okay, so active fault is usually characterized by soft materials, because of the movement. Okay, the kind of rubbing of the land of the rock blocks against each other. Okay, so that area gets kind of uh, there is ductile deformation, there is friction, and due to that the rock over there gets crushed into softer material. So usually these material can be eroded very easily if there are river channels flowing, and they can carve out different patterns and courses for themselves. So over here if you see, okay, due to this fault scarp that we can see over here, this grayish area, okay, due to the fault that is been created over here. Now this is the active fault zone currently. So you see that there is a shift in the direction of the channel, that is the stream that is present over here, that was flowing from this area towards the lower reaches. And in the right part also you can see that there is a deflection of the stream over here. Then there are different kind of features that are formed. You have sag ponds, you have scarp, obviously you have shifted stream, you have deflected streams, sometimes even springs are formed in such areas. So you can see that there was also an older fault zone. Now how will you distinguish from the older fault zones? You can see that the stream, it should have flown, I'll just erase that. So this stream that you see over here, it should have flowed in this direction, but you see over here that there has been a shift. So this was due to an older tectonic disturbance that was there, or this older fault zone. This deflection was due to an older fault zone. Now in the active fault zone, this stream over here is getting shifted. Okay, so as we said that you can have a straight scarp in such areas, active fault zones. Then you can have sag ponds, pressure ridges and shutter ridges. So these are different kind of geomorphic features that we can find in active fault areas. Then again, this entire thing is actually an escarpment. So this is actually normal fault region. This part has gone up and this part has gone down. Okay, and this scarp is a very distinctive feature of such kind of for active fault regions. Now in Himalaya, as we said that Himalaya is actually the formation is young compared to some other mountain ranges that we see across the globe. So most of the faults that are present in Himalayas are actually thrust faults. I had explained already what are thrust faults, and the growth of these faults, it's not like these long distance faults, and you can see that they go all the way up to 30 kilometers in depth also. So when they formed, it is not necessary that they formed initially stretching across for such larger distances, but with time and with continuous plate tectonic movements, these faults actually grow in length and they grow in size, and together then they form sorry larger larger length thrust faults. And because of these thrust faults, there are some features which are developed here, which again indicate the presence or the occurrence of active tectonics in these regions. So you can see over here how the kind of the fault region actually extends from one end to the other end. Okay, so this is all the way from India through your Nepal. Okay, so the entire most of the northeastern boundary of India is actually part of the Himalayan range. So how these fault actually grows? So initially the there is scattered kind of occurrences of small fault scarps, and with uh, you know uh, say with continued deformation that is happening in this region, these fault scarps actually grow laterally. Okay, and soon what happens is that the fault scarps actually connect with each other. You can see over here that this segment has connected and now it has formed like a longer fault scarp, and soon with time this will connect with this also and this also, and these two will also might get connected with time. Or right now there is an overlap where this fault scarp has come for in front of this one. There is overlap but there is no linkage, but over here there is a linkage. Okay, now this is kind of how this looks from the side. This is a fault scarp. Okay, so smaller fault scarps are formed, and if this you can have mostly in the extensional kind of feature. This is actually for the compressional. This is the compressional. You can see, so this can be formed during a thrust fault. Okay, this kind of linkage, growth and linkage. And when we are talking about this is due to the extensional, where it forms rift valleys. We had talked about rift valleys when we were studying divergent plate boundaries. Okay, so even during extensional kind of tectonic processes, you will find the growth and linkages of such fault scarps, and then these themselves form larger fault lines. and due to the deformation or the displacement along these fault scarps, you will have bigger areas that are actually undergoing active faulting. As I said, that due to the creation of multiple thrust faults in Himalayas, we get a feature called piggyback basin. So these are actually, they look like they are riding on top of the thrusted fault thrusted blocks that are present over there. So when there was no kind of no surface fault, you can see that these faults actually start from the deeper depths. Okay, so this was your main boundary thrust. Okay, so this was the main fault over here, and these smaller ones are formed due to this main boundary thrust. Okay, and this was a river that was flowing here. This was around 43,000 years ago, and with time these deep faults, they start emerging on the surface due to the growth and linkages of some fault scarps or fractures that were present over here. And then soon what we see is that these because of these thrust faults over here, this area got uplifted. Okay, and as you can see, this stream that was supposed to flow downwards, now it has changed its direction, and this itself starts forming a basin over here. Now this basin that is present over here, this is actually now called a piggyback basin. So this is actually the foreland basin. Okay, now it is actually due to progressive development of the thrust, this actually is can be carried forward by the thrust faults that are present over here. So these are also called dunes. Okay, so these piggyback basins are also called dunes. So over here what we have is actually the piggyback basin that we see, and obviously you can see the different kind of sedimentations can happen, and features can be formed due to such extensive thrust fault network that is present. So this area, you can see this length, due to thrust faulting, what happens is that the area kinds of shortens, this land area or this kind of block, the rock block that we see here, they shorten over time. So thrust faulting can compress the area that where they are occurring. And another one which is a part of these developing thrust faults is the paleo wind gaps. You can see that due to uplift event, the stream changes its flow direction. It was flowing in this direction due to maybe either uplift of this region or subsidence of this region. This can start flowing in the other direction, as you can see over here. So this area is actually called a wind gap. Now since the stream started flowing in this direction, this there will be no supply in this direction, and there will be a gap in this area. So that is the wind gap that we see. This is again an example of a geomorphic feature that is formed due to tectonic geomorphology. So that is the end for today's session. If you have any doubts, please feel free to put them up in the discussion forum, and I will reply to it. And if you have any problems in the content of the slides or in the assignment problems, you can put them up in the discussion forum as well. So I hope to see you again in the next class. So thank you for attending.